Outlier detection is a process of finding data objects with the behaviors that are very different from expectation. Such objects are called outliers or anomalies. Outlier detection is important in many applications in addition to fraud detection such as medical care, public safety and security, industry damage detection, image processing, sensor network surveillance and intrusion detection. Outlier detection and clustering analysis are two highly related tasks. Clustering finds the majority patterns in a dataset and organizes the data accordingly, whereas outlier detection tries to capture those exceptional cases that deviate substantially from the majority patterns. Outlier detection and clustering analysis used for different purposes. But in this video, we are going to cover the different categories. Majority of the object contain the dependency detection, class identification, class descriptions, and exceptions or outlier detection or outlier analysis. The first one, fraud detection. It includes credit card telecommunications, criminal activity in electronic commerce, customized marketing, medical treatments, analysis performance statistics, weather predictions, financial applications like loan approval and stock tracking. So these are all the applications are involved. This motivation for the outlier analysis object that deviates significantly from the rest of the objects, as if it were generated by a different mechanism. For ease of presentation in this video, we can refer the data objects that are not outliers as normal or expected data. Outliers are different from noisy data. Noise is a random error or variance is in a measured variable. In general, noise is not interesting in data analysis, including outlier detection. For example, in credit card fraud detection, a customer purchase behavior can be modeled as a random variable. A customer may generate some noise transactions that may seem like random errors or variance, such as buying a bigger lunch one day or having one or more cup coffee than usual. Such a transaction should not be treated as outlier. Otherwise, the credit card company would incur heavy costs from verifying that many transactions. The company may also lose customers by bothering them with multiple false alarms. As in many other data analysis and data mining tasks, noise should be removed before outlier detection. So the outlier detection versus novelty detection in the early stage is essential. Some of the applications we can mention here. First one is the credit card fraud detection, telecommunication fraud detection, customer generation, and medical analysis. Because they are suspected of not being generated by the same mechanism as the rest of the data. Therefore, in outlier detection, it is important to justify why the outliers are detected or generated by some other mechanism. This is often achieved by making various assumptions of the rest of the data and showing that the outliers detected violate those assumptions significantly. Outlier detection is also related to novelty detection in evolving data sets. So when trying to detect outliers in a dataset, it is very important to keep in mind the context and try to answer the question. Why do I want to detect outlier? The meaning of your findings will be dictated by the context. Poor data quality or contamination, low quality measurements used, malfunctioning equipment, and manual error, correct but exceptional outlier analysis. Most of the data mining method discard outliers noise or exceptions. However, in some applications such as fraud detection, the rare events can be more interesting than the more regularly occurring one, and hence the outlier analysis becomes more important in such a case. Yes. In general, outliers can be classified into three categories, namely global outliers, contextual outliers, and collective outliers. Global outliers in a given data set, a data object is global outlier if it deviates significantly from the rest of the data set. Global outliers are sometimes called point anomalies and are the simplest type of outliers. Global outliers, the points in region are significantly deviate from the rest of the data set. To detect global outliers, a critical issue is to find an appropriate measurement of deviation with respect to the application in question. Various measurements are proposed, and based on this, outlier detection methods are partitioned into different categories. Global outlier detection is important in many applications. Consider intrusion detection in computer networks. The context next one, contextual outliers. The temperature today is 28 degrees centigrade. It is exceptional. It depends on, for example, on the time and location. If it is in winter in one particular place, it is an outlier. If it is a summer day in another place, that is a normal. Unlike global outlier detection, in a given data set, a data object is contextual outlier if it deviates significantly with respect to a specific context of the object. So, the contextual outliers are also known as conditional outliers because they are conditional on the selected context. Therefore, in contextual outlier detection, the context has to be specified as part of the problem definition. Generally, in contextual outlier detection, the attributes of the data objects in question are divided into two groups. First one, the contextual attributes. The contextual attributes of a data object define the object's context. In the temperature example, the contextual attributes may be date and location. Second category is the behavioral attribute. These define the object's the characteristics and are used to evaluate whether the object is an outlier in the context to which it belongs. In the temperature example, the behavioral attributes may be the temperature, humidity, and pressure. So it can be viewed as a generalization of the local outlier whose density significantly deviates from its local data. Then how to define or formulate the meaningful. Suppose if you are a supply chain manager of all electronic shop, you handle thousands of orders and shipments every day. If the shipment of an order is delayed, it may not be considered as an outlier because statistically delays occur from time to time. However, you have to pay attention if 100 orders are delayed in a single day. Those 100 orders as a whole form an outlier, although each of them may not be regarded as an outlier if considered individually. You may have to take a close look at those orders collectively to understand the shipment problem. Given a data set, a subset of data objects forms a collective outlier if the objects as a whole deviate significantly from the entire data set. Importantly, the individual data objects may not be outliers. A data set may have multiple types of outliers. One object may belong to more than one type of outlier. Outlier detection. Outlier detection is useful in different applications. It may face some challenges such as following. First one, modeling normal objects and outliers effectively. Outlier detection quality highly depends on the modeling of normal objects and outliers. Often building a comprehensive model for data normality is very challenging, if not possible. This is partly because it is hard to enumerate all possible normal behaviors in an application. The second one is application-specific outlier detection. Technically, choosing the similarity measure and the relationship model to describe the data objects is critical in outlier detection. Unfortunately, such objects are often application dependent. Different applications may have very different requirements. For example, in clinic data analysis, a small deviation may be important enough to justify an outlier. In contrast, in marketing analysis, objects are often subject to larger fluctuations, and consequently, a substantially larger deviation is needed to justify an outlier. Third one, handling noise in outlier detection. Outliers are different from noise. It is also well known that the quality of real data sets tends to be poor. Noise often unavoidably exists in data collected in different applications. Noise may be present as deviations in attribute values or even as missing values. Low quality and the presence of noise bring a huge challenge to outlier detection. Fourth one, understandability. In some application scenarios, user may want to not only detect outlier but also understand why the detector objects are outlier. To meet the understandability requirement, an outlier detection method has to provide some justification of the detection. For example, a statistical method can be used to justify the degree to which an object may be an outlier based on the likelihood that the object was generated by the same mechanism that generated the majority of the data. The smaller the likelihood, the more unlikely the object was generated by the same mechanism and the more likely the object is an outlier. We need a special technique to identify outlier. Just modify clustering or other algorithms to detect outlier. First one, performance considerations subjective to the clustering algorithm and clustering parameters. Only certain attributes may have outlier properties, only to disqualify the entire tuple. Contamination may occur by column, not by row. Methods. There are many outlier detection methods in the literature and in practice. Here we present two ways to categorize outlier detection methods. First, we categorize outlier detection methods according to whether the sample of data for analysis is given with a domain expert provided labels that can be used to build an outlier detection model. Second one, we divide the methods into groups according to their assumptions regarding normal objects versus outliers. One, if expert labeled examples of normal and outlier objects can be obtained, they can be used to build outlier detection model. The methods used can be divided into supervised methods, semi-supervised methods, and unsupervised model data normality and abnormality. Domain experts examine and label a sample of the underlying data. Outlier detection can then be modeled as a classification problem. The sample is used for training and testing. In some applications, the experts may label just a normal object, and any other objects not matching the model of normal objects are reported as outliers. Although many application methods can be applied, challenges to supervised outlier detection include the following. The two classes are imbalanced. That is, the population of outliers is typically much smaller than that of normal objects. Therefore, the methods for handling imbalanced classes may be used, such as oversampling outliers to increase their distribution in the training set used to construct the classifier. Due to the small population of outliers in data, the sample data examined by domain experts and used in training may not even sufficiently represent the outlier distribution. The lack of outlier samples can limit the capability of classifiers built as such. To tackle these problems, some methods make up the artificial outliers. Methods of outlier detection must be careful in how they train and how they interpret classification rates due to the fact that outliers are rare in comparison to the other data sample. As shown in the diagram, raw data is supplied, then sample data, code and test new sample data, then feedback is given. Then it is applied to the algorithm, then product of trained algorithm is given, then manual verification done, then again the last one is a product scenarios, objects labeled as normal or outlier are not available. Thus, an unsupervised learning method has to be used. Unsupervised outlier detection methods make an implicit assumption that normal objects are somewhat clustered. In other words, an unsupervised outlier detection method expecting that normal objects follow a pattern far more frequently than outlier. Normal objects do not have to fall into one group sharing high similarity. Instead, they they can form multiple groups where each group has different features. However, an outlier is expected to occur far away in feature space from any of these groups of normal objects. May not be true at all the time. For example, the normal objects do not share any strong patterns. Instead, they are uniformly distributed. The collective outliers, however, share high similarity in a small area. Unsupervised methods cannot detect such outliers effectively. In some applications, normal objects are diversely distributed, and many such objects do not follow strong pattern. For instance, in some intrusion detection, computer virus detection problem, normal activities are very diverse and many do not fall into high quality cluster. In such scenarios, unsupervised methods may have a high false positivity. They may mislabel many normal objects as outliers and let many actual outliers go undetected. Due to the high similarity between intrusion and viruses, modeling outliers using supervised methods may be far more effective. Many clustering methods can be adapted to act as unsupervised outlier detection method. The central idea is to find the cluster first and then data objects are not belonging to any cluster or detected outlier. However, such methods suffer from two issues. The first one, a data object not belonging to any cluster may be noise instead of an outlier. Second one, it is often costly to find cluster first and then find outlier. It is usually assumed that there are far fewer outliers than normal objects. Process a larger population of non-target data entries before one can touch the real meat can be unappealing. The latest unsupervised outlier detection methods develop various smart ideas to tackle outliers directly without explicitly and completely finding the clusters. As shown in the example, raw data is supplied to the algorithm, then automated clusters will become the output, then manual review will be done, then it will be the production. Based methods. In many applications, obtaining some labeled examples is feasible. The number of such labeled examples is often small. We may encounter cases where only a small set of the normal and outlier objects are labeled, but most of the data are unlabeled. Semi-supervised outlier detection methods were developed to tackle such scenarios. Semi-supervised outlier detection methods can be regarded as applications of semi-supervised learning methods. For example, when some labeled normal objects are available, we can use them together with unlabeled data objects that are close by to train a model for normal object. The model of normal object then can be used to detect outlier. Those objects not fitting the model of normal objects are classified as outlier. If only some labeled outliers are available, semi-supervised outlier detection is trick trickier. A small number of labeled outliers are unlikely to represent all the possible outliers. Therefore, building a model for outliers based on only a few labeled outliers is unlikely to be effective. To improve the quality of outlier detection, we can get help from models for normal objects learned from some unsupervised methods. So this can be done in two ways. If some labeled normal objects are available, if only some labeled outliers are available. In many applications, the number of labeled data is often small. Labels could be an outliers only, normal objects only, or both. Semi-supervised outlier detection regarded as outliers applications of semi-supervised learning. If some labeled normal objects are available, use the labeled examples as a approximate unlabeled object to train a model for normal object. Those not fitting the model of normal objects are detected as outliers. If only some labeled outliers are available, a small number of labeled outliers may not cover the possible outliers well. To improve the quality of outlier detection, we can get a help from models for normal objects learned from unsupervised program. Raw data will be supplied to the program, then train the model, then sample data, code, and last new sample data. Then it is given to the algorithm. The product of trained algorithm will be the output.